Welcome to Brain Vision.
Considering a hydrogen atom in the ground state, we want to find the orbital speed. So the radius that I'm going to be using, r, is Bohr's radius. It's 5.29 times 10 to the minus 11 meters. So due to the orbit of the electron around the atom, if we're assuming Bohr's model, then the centripetal force is going to be equal to the electrostatic force that's trying to pull the atom and the nucleus of the atom and the electron together versus the centripetal force, which is just keeping it apart. If the electron isn't collapsing in on the atom, these two must be equal. So what we're going to do is we're going to set F sub c, which is the centripetal force, equal to F sub e, the electrostatic force. So doing this gives us 1 over 4 pi epsilon naught multiplied by the charge of the electron E squared over R squared is equal to mv squared, where v is the speed that we want to find, and m is the mass of the electron, since that's what's going around the atom, divided by R. So we can cancel out one of the r's on the left side, so the square goes away with this r in the denominator on the right side. And then rearranging this equation to solve for v, we find that v is equal to the square root. Since it's squared, we have to square root e squared divided by 4 pi epsilon naught times the mass of the electron, which we're using kilograms here. So this is 9.11 times 10 to the minus 31 kilograms, multiplied by r, the Bohr's radius. Plugging these values in, we find that the speed is equal to 2.19 times 10 to the 6 meters per second. We can box that in as our solution for A. Part B wants us to find the kinetic energy of this electron. So kinetic energy, which we're going to call Ke, is of course equal to 1/2 mv squared, where m is the mass of the electron, once again in kilograms, and the speed is the speed that we found in part A. So plugging these values in, we find that the kinetic energy is equal to 2.18 times 10 to the minus 18 joules. And since the energy of atoms is normally written in electron volts, we can convert this from joules to electron volts. And this gives us 13.6 electron volts, which just happens to be the ground state of the hydrogen atom. So that's a nice little check that we did this correctly. So we can box both of those in as the solution for part B. And then lastly, part C says calculate the potential energy. Well, I'm going to do the electrostatic potential energy to calculate the potential energy. And I find that using this equation, this is equal to negative K, where K is just the electrostatic constant, 1 over 4 pi epsilon naught, times E squared over R. Again, E is the charge of the electron, and R is the Bohr's radius. K is equal to 8.99 times 10 to the 9 Newton meters per coulomb. Plugging these values in, we find that the potential energy is equal to negative 27.2 electron volts. We can box this in as the solution for part C.